We're gonna have Niko from University of Rhode Island talking about infinite speed cops and robbers on grids. Go ahead.
All right, thank you very much. Thank you all for coming. So today we're going to be talking about the game of cops and robbers on graphs, and specifically the variant where the robber has infinite speed. Okay, so let's take a little introduction on what the game of cops and robbers is. Some number of cops are going to play against one robber on a graph G. So each cop and the robber are going to occupy the vertices of G. The cops are going to choose their starting positions first, and then the robber does. And then the game is played in rounds where the cops can move along edges to adjacent vertices or stay put, and then the robber does in response. And the goal here is for the cops to catch the robber. So if one cop manages to land on the robber's vertex, then the cops are going to win. Otherwise, if the robber can show that he can evade the cops forever, then the robber is going to win. Okay, so let's play out an example on this graph with two cops. And throughout, I'm going to use these blue vertices to indicate that a cop is at that vertex and a red vertex to indicate that the robber is. Okay, so maybe the cops place himself down there. The robber wants to go as far away from the cops as possible, so maybe over here. And now it's the cops' turn. So they're going to move along maybe these two edges, and that's kind of their turn. And now the robber can move, so maybe he chooses this edge to move along. And you'll notice now that the cop in the bottom row is right next to the robber. So he can kind of move over and capture the robber while the other cop stays put. And two cops can catch the robber here. And it turns out that no matter what the robber did, he was doomed on the next turn. So like I said, two cops can catch the robber since they can control the robber's row and column after one move on this particular graph. Now, the game of cops and robbers has been extensively studied through from starting in the 1980s. What we're going to be looking at is the variant where the robber is allowed to move faster than the cops. So in general, the robber can be assigned a speed S. That means he's allowed to traverse a path of length S on his turn, provided that he is not moving through any cops. So he cannot move through any cops. When S is equal to 1, we get the original game. And all the while, by the way, the cops are still only have speed 1, so they can only move to adjacent vertices. We're going to focus on kind of taking that to the extreme where S is equal to infinity. So that means that the robber is allowed to move along any path of any length, provided that there are no blocking cops. Okay, and what our goal here is to find the infinite speed cop number of any graph. And in this case, so that's denoted C sub infinity of G, and that's the minimum number of cops K, where K cops can catch the infinite speed robber, but K minus 1 cannot. Okay, so let's play on the same graph here, play two cops against an infinite speed robber this time and see if anything changes. Okay, so maybe the cops place themselves down the same way, so does the robber, and they move along the same edges. And now it's the robber's turn, and he wants to find a vertex that's kind of away from the cops, so he'll be safe on the next turn. And you'll find that this green vertex here fits that bill. It's not adjacent to any cops. And he can use this path. There's no blocking cops. He can use this path to kind of jump up there and be safe for the next turn. Now, maybe the cops move again to kind of try to block him off. But again, this can keep happening. He can find this vertex that's not adjacent to any cops and be safe for the next turn. So it turns out that two cops can catch a speed 1 robber on this graph, but more cops are needed to catch the infinite speed robber. And in particular, this shows that C sub infinity of G is greater than 2. It's actually equal to 3, but we'll talk about that a little bit later. So in order to prove that our infinite speed cop number is equal to K, we need two things. We need to prove an upper bound and a lower bound. So how do we prove the lower bound? That means we need to kind of play from the robber's perspective to evade one fewer cops, so K minus 1 cops. And on the other hand, how do we find an upper bound for C sub infinity? that's where we need to play from the cop's perspective, play K cops and show that we can catch the infinite speed robber in a finite number of moves. All right, so in particular, we are focused on grid graphs, in particular, the Cartesian product of path and cycle graphs. We're just going to talk about path graphs for the sake of speed here. So the Cartesian product of the path graph with n vertices with a path graph with n vertices. So here's an example of that. Here n is equal to 5. We have kind of a vertical copy of P5 and a horizontal copy of P5. And what happens when we take the Cartesian product is that each vertex in the first graph gets kind of a copy of the second graph, and their edges form this nice grid here. So here's kind of how it looks like without the colors. And in general, if we do this with a length n path, we're going to get n squared vertices over here in the product. Okay. So turns out that these graphs have a very nice, or kind of a trivial upper bound for the cop number, and that's equal to n. So n is the length of a row or a column, remember? So if we put cops just all across a row or a column, in this case a row, then we can kind of make progress on the robber wherever the robber places himself down. If we just tell the cops to just move down at each turn they have, robber can't move through any cops, so he's kind of forced into the bottom here, and eventually the cops will catch him. So n cops are enough to catch the robber here. Now, our project was kind of inspired by the work of Abbas Mehrabian, who worked extensively with the infinite speed game, and specifically, and many problems, but one of the things that he did was provide bounds for the infinite speed cop number for Cartesian products. And these are just kind of specific results that he has. He has much more general results than this, but we wanted to kind of improve some of these lower bounds. And that's what we did. So for the square grid, you can see the upper bound that Mehrabian had was n. Lower bound, there's a little bit of a gap there. For the cubic grid, so imagine we have the square grid, but I Cartesian product that with another path. All of a sudden now we have not n squared but n cubed vertices, and we're talking about playing on kind of a cubic grid. Upper bound is n squared, and again there's some room to work with here for the lower bound. We also worked with toroidal grids and hypercubes, but to save time, we're just going to be talking about the path graphs. Okay, so for the square grid, the upper bound was n. We found the lower bound to be n minus 1. So that's very close. And for n odd, this is a tight bound. So the idea, the proof is we want to evade n minus 2 cops, and we want to do this by showing that the robber, play from the robber's perspective, and show that the robber has enough room to reach an empty row at the end of each of his turns. And from there, he'll be able to get pretty much anywhere in the graph. Okay, so we're gonna play on, so n by n grid here, n is equal to 8. So we're gonna play against 6 cops, n minus 2. And the proof is in cases. Case 1 is kind of the bulk here. So if the first k rows or the last k rows collectively contain 2 fewer cops than there are rows, so we have 2 kind of empty rows, that's going to be kind of a nice region for the robber to find a safe vertex. So you'll notice that the first 5 rows have 2 completely empty rows. And so the robber is going to kind of chop this region up vertically in half and choose the half that has fewer cops. Here we have 1 cop. And no matter how big your region is, there is guaranteed to be a group of 4 consecutive rows within this region that has collectively at most 1 cop between them. So the robber is going to place himself down in the middle of those 2 rows, whichever one does not contain a cop. All right, so let's simulate the cops moving here. And after they move, you'll see that either the robber's current row in his little sector up here, or the row above is is empty. So he can reach an empty row here. These dark green vertices are going to indicate the robber's the path that the robber is going to take throughout the graph. So he has an empty row. He has access to an empty row, and there's still few enough cops up in the upper right-hand corner so that this empty row connects to an empty column. And then if we look at the orange region again and cut off the bottom row, there's still an empty row here. So this column connects to an empty row in the entire graph. And once we're there, the robber can move pretty much anywhere. He can get to any empty columns, any empty rows, and well, anywhere really. So he can kind of repeat this process. Now, that was case one. So if there doesn't exist this set of orange rows that contains a few number of cops, then it turns out that in case two, all the cops have to be concentrated kind of in the middle of the graph. And so the robber can find kind of a nice vertex on the edge of the graph and again, repeat the process. So n-1 are needed to catch the robber in 2 dimensions. So now we're going to talk about the 3-dimensional grid, the cube grid. And we can actually win with n squared cops. So we go up a dimension, we add a factor of n to the number of cops. So here's a cube. The idea is we just take the first plane and kind of saturate it with cops. Then the robber has to place himself down somewhere somewhere below. But again, this is kind of similar to the 2-dimensional strategy. If we just tell the cops to move down, the robber cannot move through a cop, so he's kind of sandwiched until at the end he's finally caught. So n squared is enough to catch the robber. We can actually do a little bit better though. If we take this plane and we kind of slice it through the graph of the cube, and we put cops on the intersection of the plane, this little hexagonal intersection, this actually cuts the graph exactly in half, and the robber is going to have to choose which half of the graph to play on. So here's an example of we have the cops just kind of saturating this hexagonal plane. So maybe the robber chooses the left half of the graph to place himself down on. If we add just a few more cops, we can tell all of the cops to move down. And then we have excess cops on the bottom, so they move up within in the span of a few moves. And then we move down again, and we kind of can repeat this process in a finite number of moves and catch the robber. He's going to be sandwiched again at the bottom. And this takes about 3/4 n squared cops, so it's a little bit of an improvement there. And this idea of cutting through with a oblique plane and cutting the graph in half, this idea extends to the upper bound of cop numbers of higher dimensional grids as well. Okay, so for the lower bound, the best lower bound we have currently is that we can show that the robber can evade 2/3 n squared cops. This argument we feel could be pushed a little bit, so there is some room for improvement. But the idea is that the robber is going to cut the graph up into halves and then quadrants and then finally octants and choose the octant that has the fewest number of cops. And after the cops move, he's going to find a safe vertex here. After the cops move, he's going to be able to find, again, a empty row. And from there, he will be able to get pretty much anywhere. Okay, so the infinite speed cop number of the cube is between now 2/3 n squared and 3/4 n squared. All right, so a few more results that we came up with are we looked at the toroidal grid. We got the asymptotics here. We improved the lower bound to be about 2n. And from here, this used kind of similar ideas to the square grid strategy. We also have tentative work on the, or a tentative result on the lower bound for the hypercube. In Morabian's result, he had an n to the 3/2 in the denominator. We have an n times L and n. And this actually uses a different technique. It uses the idea of a potential function on the vertices of your hypercube. Okay, I think that's all I have time for. So thank you very much to the organizers of this conference. Thank you to my advisor, Dr. Kindersley, for working with me. And thank you all for coming. Are there any questions?
Yeah, let's thank our speaker. Feel free to unmute yourselves or use a Zoom React. Thank you. That's a great talk. A lot of fun.
The C infinite number of a graph, how is that related with the domination number? Because I feel like if you set the cops up to dominate the graph, or barely almost dominate the graph, I was just wondering if you knew any bounds, how they connected in some way.
Yeah, absolutely. So the certainly the domination number, sorry, I think I went too far. The domination number of the graph is, oh, I can't find it anymore, is very closely related. So if you have, here we go. If you have a dominating set, if you place the cops down, then they'll be able to win within one move, no matter where the robber goes. So the domination number is an upper bound on the infinite speed cop number, and in fact on the cop number as well. So here we have the infinite speed variant. If you just replace infinite with just one speed, that's the typical, just the cop number of the graph that we talk about. Yeah, so the cop numbers are always upper bounded by the domination number, for sure.
Are there examples where they're like arbitrarily different? Like the domination number is like way you didn't need that many cops at all or whatever, you know?
Yes, absolutely. So in this graph actually, so this is what's called, this is the K3, Cartesian K3. It's also called the Rook's graph. So you can move like a rook in chess. And this is a 3x3, but in n by n graph, the domination number is n, because you need a cop in every column to kind of, or every row to dominate the graph. But the cop number is equal to 2, because wherever, kind of the same idea here, wherever the robber is, I just kind of look at my row and column, and then if the robber has speed 1, then he is confined to his row and column, and the cop number can, or the cop can catch him. I'm not, off the top of the head, I can't think of any infinite infinite cop number examples, but that's certainly one for the regular game.
Thank you. Well, I have another question. If not,
Sure.
I'll pause to make sure no one else. So is there a version sort of in between? You said infinite, so it's an infinite path. But what if you oriented your grid and you can move only you can move infinitely, but only east, right? Or like move infinitely, but only north, sort of like kings trying to catch a queen on a chessboard.
Yeah, there's absolutely some variants that are very similar to chess. And I haven't actually worked on directed graphs, but I know that one of my colleagues has. But to go back to your chess analogy, there's something called a variant that I worked on in undergrad called lazy cops and robbers, where the cops, the robber still has speed 1, but the cops, only one of them is allowed to move per turn. So that is kind of similar to chess, where you only get to move 1 piece per turn. And that's actually very interesting. Yeah, there's a few introductory papers out there if you're interested. But yeah, but yeah, that's but to answer your question, yeah, I haven't worked with directed graphs, but that is certainly interesting.
Thank you.
Are there any variants out there where maybe there's more than one robber, or like the cops can move at different speeds? You've got like a sheriff and a cop, or something like that.
Absolutely. So I don't know how extensively they've been studied, but I kind of think of this as a spectrum where you can vary both the robber's speed and the cop speed. And kind of the extreme is where we push the robber speed to infinity and leave the cops just kind of at 1. But you can do the other way too. You can look at where the robber has speed 2 and the cops also have speed 2, or they have speed 3, and multiple robbers. Right. That is certainly a variant. I don't know of any results off the top of my head, but certainly a variant you can look at.
Thanks.
Yeah.
I have a question.
Sure.
So, is there a version for weighted graphs? Like there is some allotment to the cops and the robbers, and for every move they make, there is some cost and like a
Yes.
finite version.
Yes, for sure. Again, I don't have any results off the top of my head for that, but yes, that is certainly something you can look at. And also related to that, there's a variant where you assign a probability to the cops' move for each of their neighbors, and so it's kind of like random cops and robbers where they make a random move based on their adjacencies, and see what's the likelihood of catching the robber in a finite number of moves. But yes, there is weighted cops and robbers as well. And again, this is kind of a very rich field. There's a lot of different variants to look at. So for sure, all of these are studyable.
Okay, thanks. Could you just point out some reference for getting a broader overview of this?
Oh, sorry. Could you say that one more time?
Could you please refer me something that would give me a broader overview of this?
Oh, absolutely, for sure. Yep, I can link you some resources for sure. There's a I can do that.
All right, I think we should transition to our next speaker now. Let's thank Niko one more time.
Yeah.